Okay. Hi, everyone. I'm here to talk about some joint work with Jason Brecht, Zach Kincaid, and Tom Reps. So what I first want to do is I want to take an overview of what we call algebraic program analysis, or sometimes thinking about analysis in the style of Tarjan. So the basic idea is we have our original representation, some source code here. And what we're going to do is we're going to take and learn a path expression over that the control flow graph of that original program. And essentially, the path expression is going to be a regular expression with regular expression operators, such that when you interpret the regular expression in terms of the language it generates, you're going to contain all feasible program paths of the original program and perhaps some additional ones. So we're going to take this path expression and we're going to feed this into a semantic algebra, which you can think of as sort of like an abstract domain. So the semantic algebra has circle plus, circle times, and circle star operators, which respectively approximate the regular expression operators. And then essentially what we're going to do is we're going to reinterpret the path expression in our semantic algebra, and that'll give us an interpretation in our semantic algebra, which will be our resulting summary. So we'll just go through a bit of an example here. So the example algebra we're going to consider is two vocabulary transition formulas with the following operations. So for the choice operator, we're going to use just logical disjunction. For the extend operator, we'll have this sort of relational composition where we project out the middle variables. And then the interesting one is when we reach a star, we're going to abstract our formula we have for the loop body to some sort of approximating octagon, and then compute the transitive closure of that octagon. So for example, for this particular program here, we'll have a simplified path expression just for the loop. And so the basic idea is I'm going to use A to represent the path where you do not take the then branch, and has this corresponding transition formula. And then we'll use B to represent the path where you do take the then branch, and has this corresponding transition formula. So then basically what we do to analyze this loop is we're going to replace A and B with phi A and phi B, and replace the regular expression operators with the operators from our semantic algebra. So then, since we have our choice operator being logical disjunction, we'll just go ahead and do that. And now we need to evaluate this loop body. And so what we're going to do is abstract this disjunctive formula here to some approximating octagon. Now the important thing to note is that in one disjunct we have y staying the same, and on the other disjunct we have y getting increased by 1. So when we abstract to the octagon, we're going to lose the precise information about what happens to y. It can either go by 1 or stay the same. Nonetheless, if we continue and compute the transitive closure of that octagon, we'll get a formula that looks like this. And then when we combine that with the initial information about the values of x and y before the loop, as well as the loop terminating condition, we're going to be able to conclude that x is 100 after the loop. However, we're only able to conclude that y is somewhere between 50 and 150, which is unable to prove this assertion. So let's take a closer look at this particular example. So essentially what we did is we had this path expression, we fed that into a semantic algebra, and we got this resulting summary. But one observation that may be able to be made is that if we interpret the language that this path expression generates, we contain many additional paths that are not actually feasible in the original program. So namely, any path with the subword BA in the original program is not possible. This is reflected by the idea that this formula here is unsatisfiable. So another way to think about this is that for the then branch to be taken in this original program, we need x to be bigger than 50, and x is increasing, so thus if you take the then branch right now, the next iteration you'll have to continue to take the then branch. So essentially what we can do is we can refine this path expression and remove some of those infeasible paths. So essentially if we do, we can rewrite this path expression as something that looks like this, something like A star, B star. And the idea here is that this path expression is equivalent to the original one in the sense that we've only removed infeasible paths, but this one also more closely represents the actual feasible paths of the program. But more importantly for this talk is if we feed this resulting path expression into our semantic algebra, we're going to get an exact answer because the phi A and phi B just happen to be octagons already. And so essentially this is going to allow us to conclude that x and y will be 100 at the end of the loop. So what we consider this process to be is sort of control flow refinement. So this was sort of our original picture we had previously. But now we're just going to add an additional step in here, which we're given sort of our original path expression, which is defined by the sort of the syntax of the program. And now what we're going to do is we're going to detect and remove infeasible paths from that original path expression to generate a new path expression, say r prime. And we say R and R prime are still sort of representing the same set of concrete actions because we're only removing infeasible paths. However, if you interpret those paths in terms of the languages they generate, we've actually reduced in terms of the languages. But one of the questions that we asked for this work is, you can imagine doing this control flow refinement and analyzing R prime as opposed to the original path expression that you were generated. But what if you compared that result, say S prime, with the result of analyzing just R by itself? So as we see sort of from the previous example, as well as from the literature, refining often creates better answers and better summaries. However, can we ask the question, can refinement ever produce worse summaries for us? And sort of counterintuitively, the answer is yes. Refining can actually produce worse analysis results. So just to give a quick sort of maybe contrived example, we can have this particular example. And so this program has 3 paths through it, and we'll use A to be the first path, B to be the second path, and C to be the third path. And so essentially, skipping forward a bit, if we take this path expression and feed it into our semantic algebra, when we abstract to a loop body, we're going to see that I and j are exactly increasing by 1 because I and j increase by 1 on all paths through the loop. And essentially what that means is when we compute the transitive closure, we're able to see that I and j increase by some amount k, and this is good enough to show that I and j will be equal at the end of the loop. However, it's also the case that the subwords AC, BA, BB, and CC are infeasible in this original program. So what happens here, if we take this alternative path expression and feed it into our semantic algebra, we're going to get some formula like this here when we get ready to evaluate the star. And unfortunately here, we have 2 disjuncts, and on one disjunct, I and j go up by 1, and in the other disjunct, I and j go up by 2. So when we abstract to the octagon, we're going to lose the precise information about what happens to I and j. And unfortunately, the summary that we're going to be able to conclude from this alternative regular expression is not going to be enough to prove the assertion. So sort of what happened here? Why should we expect this? So sort of previously, when we were doing control flow refinement, we were reducing the path expression in terms of the languages that they generate. Such a transformation is based on sort of the algebra of regular expressions and justified by this algebra. Instead, what we're really concerned with is not about the languages, but about the analysis precision. So instead, we need to be focused on the algebra of our abstract domains, not the algebra of the regular expressions. So this is where we come in. What we're going to do is we're going to introduce an algebra for understanding this analysis precision. We call this the pre-Kleene algebra. And then we'll use the pre-Kleene algebra to derive an algorithm for control flow refinement that gives us precision guarantees. And so this means essentially that we're going to be safe to do the control flow refinement procedure and not have to worry about getting any worse results. All right. So before I talk about the pre-Kleene algebra, I'll talk about the Kleene algebra. So this is axiomatization due to Cozen. So the basic idea is you have an algebra with a signature, and if you remove the star, you have an idempotent semiring, and which gives rise to this partial order here. You can use this partial order to define a set of star axioms. It's not super important to understand all the details of these star axioms. It just essentially allows for the natural interpretation that A star gives you 1 plus AA, etc. So this was the algebra of regular expressions. So an example is the regular expressions over, say, some alphabet, say sigma, with union being or plus being union, dot being concatenation, and star being the Kleene star. So we talked about the algebra for regular expressions. What are the algebra that we're going to use for abstract domains? So one of the observations that we make is that a Kleene algebra is too strong. The axioms imply that A star is equal to some least fixed point, which for a lot of the domains that we're interested in is not computable. So what we need to do is we need to sort of relax our axiomatization a little bit for the abstract domains that we're considering. So this is what we do. This is the pre-Kleene algebra. So a pre-Kleene algebra has the same signature as a Kleene algebra. If you remove the star, you also get an idempotent semiring with the same partial order. However, we have a different set of star axioms, which are given here. It's not super important to know all the details for each of the individual star axioms, but the important thing to know is that you can derive all these axioms from the axioms of a Kleene algebra. So that means that the pre-Kleene algebras are strictly weaker structures than Kleene algebras. So as an example, the algebra given previously was an example of a pre-Kleene algebra, but it's not a Kleene algebra. So what's a little bit more of the relation between pre-Kleene algebras and abstract domains? So not all pre-Kleene algebras, or not all abstract domains are pre-Kleene algebras. However, we feel that our axiomization plays the balance appropriately to allow for some non-trivial refinements, but also allowing for a wide class of interesting abstract domains. There's some more discussion about this relation in the paper, and so I implore you to read it to get more information about that. But the important thing is that if you have domains which do satisfy the axioms of a pre-Kleene algebra, we see that we can use the order of the pre-Kleene algebra as a sort of a guard to understand that we're not going to lose analysis precision. So essentially, if we're given some path expression R and we give some alternative R prime, we have this guarantee that R prime will be no worse and perhaps better than R. So this theorem gives a sort of a signature for this procedure that we're going to use for designing a control flow refinement algorithm. So the basic idea is we're going to be given some path expression R and some set of infeasible words. We want to produce another regular expression, say R prime, with the following properties. We're going to say R prime is equivalent to R modulo these infeasible subwords. So essentially, we're just removing these paths with these infeasible subwords. We want to reduce in terms of the languages. But this third property is what distinguishes us from previous work. And this says that we're only going to produce regular expressions which reflect the order of the pre-Kleene algebra. And this is what allows us to give our precision guarantees. So before we focus on the general problem of refining any path expression, we're just going to focus on the goal of refining a single loop. But before that, we want to also, before we actually go into the algorithm, we want to know, okay, we want to produce an expression R prime that reflects the order of the pre-Kleene algebra, and we want to know what properties must R prime satisfy. So what we show in the paper is that R prime has to satisfy what we call the equal unrolling property, which essentially means that R prime has star height 0 or 1, and for every substar of R prime, that star body, when interpreted as the language, has to consist of A1 plus AK unrolled some equal number of times. So for example, using this theorem about the equal unrolling property, we can directly conclude that we have the precision guarantees that we're looking for with A star B star, because A star B star satisfies the equal unrolling property. However, we don't have the precision guarantees with the other regular expression we had previously, because that does not satisfy the equal unrolling property, because we have sort of A comes from the loop unrolled once, but BC comes from it unrolled twice. So this gives rise to our loop refinement procedure. So just sort of quickly going through this without too much detail, the basic idea is we're going to create a graph with the vertices with labels A1 through AK, and then we're going to add directed edges in this graph for every feasible edge between each one of these summands. So you could create, for example, some sort of graph like this, and sort of the basic idea is that we need a procedure that's going to produce a regular expression which satisfies the equal unrolling property. So the basic idea is we're going to detect strongly connected components and refine that with a single star. So we can get something like this, and there's some more details about how exactly you do that, but you're eventually going to be given some sort of DAG, which you can directly compute a path expression which satisfies the equal unrolling property. Okay, so we can use that refinement procedure for a single loop to refine arbitrary regular expressions. So the basic idea is we have this algorithm which will recursively call itself for these plus and dot operators. However, for the star, what we're going to sort of do is we're going to recursively call the refinement procedure on each individual summand of that loop, and then we're going to syntactically refine that single loop using the previous procedure, and then substitute back in our refined summands in a resulting refined expression for the loop. So essentially the important detail, though, is that we show that if you give an arbitrary regular expression to this procedure, you're going to reduce in terms of the language, and you're also going to reflect the order of the pre-Kleene algebra. So now I just want to sort of give some experimental results. So we implemented these procedures. The basic setup here is that we have 222 programs coming from the literature as well as a lot of the SVComp benchmarks. And then so the goal is for each one of these runs, we show how many assertions each analysis was able to prove. Higher numbers are better. We also timed each analysis in seconds. So for the analysis that we did run is the first one was the KCBR domain, which is sort of a framework we presented at POPL last year. So the important thing here is that this is actually does not satisfy all the axioms of a pre-Kleene algebra, but our refinement procedure still provides non-trivial refinement and allows for a decent increase in assertions proved. We also implemented this domain we call the ACI domain, which is a pre-Kleene algebra, so it does come with our precision guarantees. And then also to give context to these experimental results, we compared with some state-of-the-art model checkers who do quite well on the SVComp benchmarks. So sort of the main takeaway, I'd say, from this table is that when you compare adding refinement to one of these domains as compared to not adding a refinement, you get about a 25% increase in the number of assertions proved at the cost of about a 50% increase in analysis time. A lot of this comes from this increase in analysis time comes from actually the feasibility checks that we're making to determine actually with respect what subwords are we making our refinements with respect to. So just sort of in conclusion, in this talk I talked about basic algebra for understanding analysis precision. We called that the pre-Kleene algebra. I also gave an algorithm which refines path expressions according to these properties, and the third one being the important one. That gives us the precision guarantees. This algorithm allowed us to prove 25% more assertions at an increase of about 50% in analysis time, and I think I'm going to stop there.
Very much. I'll start with a question in Slido. How does your approach compare with more standard abstract interpretations with trace partitioning or dynamic partitioning?
Yeah, so our most differing from sort of standard abstract interpretation is we don't necessarily have some sort of iterative procedure to compute fixed points. So the basic idea for that is that we're not sort of continually having to iteratively refine during the analysis. We sort of we're refining once at the beginning and then just doing a straight computation and a straight over approximation of the program.
Okay, another question, is there a chicken or an egg problem here? The analysis to determine feasibility of a refinement might be sufficient for the overall analysis goal.
Yeah, that's a good question. So that's actually, I think, one of the advantages of our approach. So it's not exactly the way we presented it here, but we can actually sort of bottom up do the summary to the point where we can use the summaries at lower level of the sort of lower level of the expression tree to determine infeasibility paths for refinement at higher levels of the star. And so the reason we're able to do that is because like this algebraic framework allows the analysis in this bottom-up sort of uniform way. So I think that's actually an advantage of our approach.
There is an analogy with the trace partitioning of Rival and Mauborgne, but they have the possibility to join paths after a case analysis they joined. I have not seen how you can join paths when you have split already.
You mean, what do you mean join after?
That is, you take two paths that make a case analysis, but it may happen that the analyzers are the same, so you want to join to go and not consider two
right.
cases.
So if the analyses are the same, we should be able to sort of join when we do the logical disjunction. They'll come together.
And you should be able, but how do you do it?
The logical disjunction. Well, our domain is just our formulas, and then so we're going to, when they come together, they'll just sort of trivially go to the one disjunct. And then what the important thing is that we're doing is when we reach another star, perhaps at a different level, we'll introduce the abstraction by sort of going to some abstract octagonal relation. We can talk more after.
More questions? I have one. So in proving dependency properties that involve, say, pairs of runs of programs, one's often to get effective analyses, you want to figure out alignments of two pairs of runs. So it struck me that concurrent Kleene algebra that adds the operator of things being in parallel could be conceivably applied here.
That would be, yeah, that's a very interesting an idea and something that would be very helpful that we're sort of interested for sort of like various hyperproperty verifications. So, I'm not exactly sure how to do it, but it's an interesting idea.
Any more questions? Okay, let's thank the speaker.